You finished the machine learning series. 3 capstones. Every core algorithm covered. Now the question everyone asks next. What about deep learning? What are neural networks actually doing? Not the marketing version. Not the magic black box. The actual mechanics. Weights, biases, forward pass, backprop. Hi, I am Mahaz, an AI engineer. This is the Deep Learning series. We build every concept from scratch, starting today with a single neuron. Episode 1 of the Deep Learning series. No assumed deep learning knowledge required. Why deep learning? You already know linear regression and random forests. Why do you need this? Classical ML models are powerful, but they require you to handcraft features. You decide what to feed in. Neural networks learn their own features. Given enough data, they discover the relevant patterns themselves, without you specifying them. Image recognition. You do not tell the network about edges or corners. It learns to detect them. Language models. You do not handcode grammar rules. The network learns the statistical structure of language. The price. More data, more compute, less interpretability. The payoff. State-of-the-art performance on tasks where handcrafted features fail. Start at the bottom. 1 neuron. A neuron takes some inputs, multiplies each by a weight, sums them up, adds a bias, and passes the result through an activation function. Written out. Output equals activation of the quantity W1x1 plus W2x2 plus B. The weights say how much each input matters. The bias shifts the output up or down regardless of the inputs. The activation function introduces nonlinearity. Without it, stacking neurons is the same as one linear equation, no matter how many layers you add. This single neuron is the perceptron. It is the building block of every neural network ever built. Activation functions. 3 you need to know right now. Sigmoid. Maps any input to a value between 0 and 1. Used in the output layer for binary classification. Problem. Gradients vanish for large inputs. Tan. Maps any input to a value between -1 and 1. Zero-centered. Still has the vanishing gradient problem at the extremes. ReLU. Rectified linear unit. Output is 0 for negative inputs, equal to the input for positive inputs. Simple. Fast. Solves vanishing gradients in most hidden layers. For hidden layers, default to ReLU. For output layers, use sigmoid for binary classification, softmax for multiclass, and no activation for regression. Stack neurons into layers and you get a multi-layer perceptron, the simplest deep network. Input layer. Your features, 1 node per feature. No computation happens here, just data entry. Hidden layers. Each neuron takes all outputs from the previous layer, applies weights and bias, runs through an activation function. Output layer. 1 neuron for regression or binary classification. 1 neuron per class for multi-class problems. Each connection between 2 neurons has exactly 1 learnable weight. A network with 1 hidden layer of 64 neurons and 10 input features has 640 weights, just in the first connection. Training finds the right values for all those weights. That is the learning. The forward pass. Data enters at the left, prediction exits at the right. Step 1. Your input vector multiplied by the weight matrix of layer 1, plus the bias vector of layer 1. Step 2. Pass that result through the activation function of layer 1. This is the hidden layer's output. Step 3. Repeat for every subsequent layer. The output of each layer is the input to the next. Final step. The output layer produces a single number or a probability vector. That is your prediction. The forward pass is just matrix multiplication and function application. Nothing mysterious. The network is a composition of functions. After the forward pass you have a prediction. How wrong is it? That is what the loss function measures. For regression, mean squared error, the average squared difference between prediction and true value. For binary classification, binary cross-entropy. It penalizes confident wrong predictions heavily. For multi-class classification, categorical cross-entropy. Same idea extended to multiple output classes. The loss is a single number. Lower is better. The goal of training is to make this number as small as possible. Think of the loss as a landscape, a surface of hills and valleys. Training is finding the lowest valley. Backpropagation. How the network learns from its mistakes. You have a loss. You want to reduce it. The question is, which weights should move and in which direction? The answer comes from calculus. Compute the gradient of the loss with respect to every weight. The partial derivative tells you the slope. If the gradient is positive, the weight is making the loss larger. Move it in the negative direction. If the gradient is negative, move in the positive direction. This is gradient descent. New weight equals old weight minus learning rate times gradient. Backpropagation is the algorithm that efficiently computes those gradients. It uses the chain rule of calculus, working backwards from the output to the input. You do not implement backprop by hand. PyTorch and TensorFlow compute it automatically. But understanding what it does is not optional. Your first neural network in PyTorch. 10 lines of real code. Import torch and torch.nn. Define your network as a class that inherits from nn.module. In the constructor, define 2 linear layers using nn.linear. First layer, input features to 64 hidden neurons. Second layer, 64 neurons to 1 output. Define the forward method. Pass input through layer 1. Apply ReLU. Pass through layer 2. That is your forward pass. Instantiate your model. Choose a loss function, nn.bc with logits loss for binary classification. Choose an optimizer, torch.optim.atom, learning rate 0.001. Training loop, 0 the gradients, run the forward pass, compute loss, call loss.backward, call optimizer.step. Repeat for every batch, every epoch. That is it. Every deep learning project from here on uses this exact loop. Recap, what a neural network actually is. A neuron, weighted sum of inputs plus bias, passed through an activation function. A network, layers of neurons. Input layer, hidden layers, output layer. Forward pass, data flows left to right through the layers. Output is your prediction. Loss, a number measuring how wrong the prediction is. Lower is better. Backpropagation uses the chain rule to compute gradients of the loss with respect to every weight. Gradient descent. Update each weight by a small step in the direction that reduces the loss. PyTorch defines the network, automates backprop, runs the training loop. Deep Learning Series. Episode 1 done. Next episode, activation functions in depth. Why ReLU beats sigmoid in hidden layers. Leaky ReLU, YeLU, JeLU. When each one is the right choice. Challenge for this episode. Take the PyTorch network and add a third hidden layer with 32 neurons. Does validation accuracy improve? Train it, measure it, post the numbers in the comments. I read every one. Subscribe so you do not miss the activation functions episode. It drops very soon. Code is in the repo. Link in the description. A neural network is not magic. It is a function. A very large function with a lot of adjustable numbers. Backpropagation adjusts those numbers, gradient by gradient, until the function gets things right. You now understand the core loop. Everything else in deep learning, CNNs, transformers, diffusion models, is built on exactly what you just learned. Activation functions are next. Subscribe, and I will see you there. Drop your hidden layer experiment result in the comments. See you in episode 2.